Hello everyone, my name is Jack Eagle, and today we're going to be talking about methods of time series forecasting in R. Before we get into the meat and potatoes of this presentation, let's give a brief overview of what we'll be discussing today. One of the time series principal uses is to produce forecasts for future time periods. Using data gathered on a single subject over the course of several time periods, one can create a projection for what values that subject will display in future time periods. There are a number of time series forecasting methods, each one having its own benefits and drawbacks. After reviewing the basic structure of a time series, some of these methods will be discussed in detail. These include the naive forecast, the seasonal naive forecast, the simple exponential smoothing method, Holt's method, and Winter's method. These forecasts will be compared to one another using several accuracy measures to determine the strength of their forecasting abilities, as well as which techniques work best under certain conditions. And their outputs will be displayed using R. So without any further ado, let's get into it. First off, let's discuss the time series. Time series data is data collected on a particular individual over a sequence of time periods. It is a cornerstone of modern statistical practice and regression analysis, and it is used frequently in several industries and economic sectors. For example, data could be collected on the sales of a particular firm over the course of 20 years, with the data point recorded every 3 months. Two important components of time series analysis are trend and seasonality, though not every time series displays these concepts. A trend is a tendency for the time series to move upward or downward over many time periods. Returning to the previous example, the firm's sales could be increasing steadily over those 20 years, indicating a trend in the data. These trends can take on various patterns, such as linear trends or quadratic trends. Seasonality is the existence of a seasonal pattern that occurs when a time series is affected by seasonal factors, such as the time of the year or the day of the week. It is possible that the firm experiences higher levels of revenue during the first and fourth quarters of the year and lower levels during the second and third quarters. The existence or non-existence of trend and seasonality in a particular time series plays a large role in determining which forecasting models are appropriate for that series. Let's move on to a general overview of forecasting. When it comes to forecasting using time series, the primary goal is generally to produce forecasts of the dependent variable for future time periods. We want to project what values of the dependent variable the subject will display in future time periods. Now, there are two main approaches that exist to assist in this endeavor. One is to identify variables related to the dependent variable in a causal manner and develop a causal regression model using them. This is the causal method. The other is to identify movement patterns and past values of the response variable and extrapolate them into the future using an extrapolative regression model. This is the extrapolative method. Explanatory variables are used in this particular approach. They are not causally related to the response. Each approach has its own benefits and drawbacks. We'll look solely at extrapolative regression methods, as these are more common in statistical analysis. They also make for simpler variable selection and data collection because only past values of the response variable are required, whereas causal models require identification of and data on variables related to the response in a causal manner. An effective way of evaluating the accuracy of forecasts is to consider how well a model performs on data that was not used when fitting the model. Upon the selection of a model, statisticians will often separate the available data into two sections, the training data and the testing data. The former set is used to craft the forecast, and the latter is used to test its accuracy. As a general rule of thumb, the testing data is about 20% of the total sample. There are a number of particular values used to evaluate forecast accuracy. Many of them deal with summarizing forecast error, which is the difference between an observed value and its forecast. These methods include calculating the mean absolute error, MAE, and the root mean squared error, RMSE. MAE and RMSE are scale dependent, meaning that they are based solely on the forecast errors and cannot be used to compare between series that involve different units. Calculating the mean absolute percentage error, MAPE, which is the average ratio of the absolute value of the forecast errors to the absolute value of the response value, is another technique. Percentage errors are unit-free and are thus used to compare forecast performances between data sets. Finally, there's the mean absolute scaled error, MASE, where the scaled error is based on the training data, MAE, from a simple forecast method. Naturally, the best forecasting method will be the one which displays the smallest values for these terms. With all that out of the way, let's move on to our forecasting methods. There are a number of simple forecasting methods that do not require much work to explain or compute. These are called baseline forecasting methods, and one of the most common methods in this category is the naive forecast. With this type of forecast, all forecasts are set to the value of the last observation. For a time series with t observations, y1, y2, all the way to yt, the forecast for period t plus h is equal to the value at period t. Naive forecasts are often the best forecasting method for time series involving economic and financial data because these data sets follow what is referred to as a random walk. These random walk models generally display long periods of apparent trends up or down and sudden and unpredictable changes in direction. Because of this random nature, other extrapolative methods may not be well suited for these datasets in the same manner as the naive forecast. That being said, there are many time series that do not follow a random walk and could be better forecasted using a more complex model. The naive forecast serves as a baseline method to compare to these other models. The following example will illustrate the use of the naive forecast in R. The dataset analyzed here includes 20 monthly sales observations in thousands of units of computers produced by the XYZ Corporation. The data displays no trend nor indication of seasonality. I have the data included in this table right here. The red numbers are what we use as the training dataset, and the green is what we use as the testing dataset. Before loading the data into R and running analyses upon it, the forecast package must first be installed. This package allows the user to run several different types of forecasts in R. It also includes functions to graphically display them alongside the time series and evaluate their accuracy. The package ggplot2 has also been installed so as to enhance the graphical presentation of the data. As mentioned previously, the training dataset will consist of the first 15 months, leaving the remaining 5, the green numbers, to comprise the testing data. The data is loaded into R and converted into a time series using the ts command. Using the window command, the training set is created. Then, using the naive command included in the forecast package with h, the value that represents the number of desired forecast periods set equal to 5, a naive forecast is created. Finally, the autoplot command creates a graph showing the actual sales for all 20 observed models and the forecasts for the 5 months in the testing set. Here we can see the code for this example. We have opening up the libraries, then we have fitting the time series right here, followed by setting up the training data set, the naive forecast, and then finally the plot. Here we have the graph for the naive forecast for this example. As shown by the graph, the naive forecast suggests that the next 5 months will have sales equal to the value of sales in the 15th month, which was 18,000 units. The prediction intervals, which are not displayed on the graph, grow wider as the forecasted periods become farther and farther removed from the time frame of the dataset. Since these intervals include negative sales values, it is not worthwhile to interpret them, but their increasing width indicates that there is a relatively high level of uncertainty regarding the accuracy of some of these forecasts. Still, as touched on previously, the naive forecast is often primarily useful, more so as a baseline to compare to other forecasting techniques, than as a truly accurate method in its own right. Moving on, let's discuss the simple exponential smoothing method, or SES. Exponential smoothing methods compute a weighted average of all past observations, with the most recent observations weighted most heavily. This process is what is known as smoothing the series. For data which does not showcase trend or seasonal variation, the simple exponential smoothing method works best. The formula for this forecast is fairly similar to computing a geometric sum of past observations. To compute a forecast for period t+1, the formula is written here, as you can see, or it could alternatively be written like so. Alpha is the value of the smoothing parameter. This value falls between 0 and 1, and it is selected either by the forecaster or by the statistical program running the analysis. Should this value be closer to 0, then more weight is given to observations farther in the past. By contrast, a value of alpha closer to 1 would cause more weight to be given to more recent observations. When alpha is equal to 1, then the simple exponential smoothing method will have the exact same forecast as the naive forecast. Returning to the XYZ Corporation example, a simple exponential smoothing forecast is run using the SES command, as we can see down here. We can also see comparisons that are run between the naive method and the simple exponential smoothing method right here. We'll come back to that a little later. Graph 2 right here showcases the forecasts for the next 5 months using the simple exponential smoothing method. Like the naive forecast, the forecasted value of sales, approximately 8,600 units, is the same for each of the forecasted time periods. However, the prediction intervals remain constant as time progresses. To evaluate the two methods, summaries of their forecast errors are computed and compared to one another. Let's go back to what I was talking about earlier, this example right here. R uses the accuracy command, which comes from the forecast package, to accomplish this. After the window command is used to create the testing set, thus providing something to compare to the forecasts, the accuracy command is run on both methods. Several accuracy standards are thus calculated, including the one discussed previously. This table right here displays these values. As we can see, the simple exponential smoothing method has smaller values for all 4 accuracy measures than the naive forecast does, demonstrating that it is the more appropriate method in this scenario. It should be noted that the simple exponential smoothing method is not always more appropriate than the naive method. For example, if the training set for this data had encompassed the first 16 months and the testing set the last 4, then the naive forecast would be found to have smaller error values. However, in general, the simple exponential smoothing method is preferable given its more extensive procedures. As mentioned previously, there are other methods of exponential smoothing. These tend to be used in place of simple exponential smoothing when a series displays a trend or seasonality. Holt's linear trend method, also called double exponential smoothing, was created to extend simple exponential smoothing to allow the forecasting of data with a trend. This method utilizes the smoothing performed by simple exponential smoothing and repeats the process a second time, with the difference between the single smoothed values and the double smoothed values providing a measure of the trend. This process can be written with the following 3 formulas, which we see here. In the first equation, LT represents an estimate of the level of the time series at period t. The second equation uses capital T to denote an estimate of the trend of the series at time t. Gamma serves as the smoothing parameter for the trend. The level equation shows that LT is a weighted average of YT and the forecast for time t represented by L t-1 plus capital T t-1. Meanwhile, the trend equation shows that capital T is a weighted average of the estimated trend at time t based on LT minus LT-1 and capital T t-1, which is the previous estimate of the trend. Finally, the forecast for time t plus m is the level at time t plus m times the trend component at time t. To illustrate how Holt's method compares to simple exponential smoothing when it comes to time series with a trend, another financial data set is studied. This time series contains information on the amount of money in billions of dollars spent on new construction in the United States, and the data displays a clear positive trend. Forecasts will be constructed for the last 3 years of the data, 1999 to 2001, using both exponential smoothing methods. As you can see, we have the training set in red and the testing set in green. So we first decide to set up a forecast for the simple exponential smoothing method. Here's the code. It's fairly similar to the simple exponential smoothing method we used for the other example, except this time it's for a new example. This graph showcases the results of the simple exponential smoothing method. As in the previous example, the forecast remains constant for all 3 years, despite the fact that the real values displayed for those years are continuously increasing. This constant forecast value comes out to about $705.69 billion. In this case, the prediction intervals are not constant, but they increase at a rate that is equal on either side of the point forecast. To obtain the Holt forecasts, the Holt command is used. We can see that right here. This graph shows the Holt forecasts for these 3 years. Because this method accounts for trends, the forecasts increase as time goes on. For 1999, the forecast is approximately $735.21 billion, and the 2000 forecast is roughly $766.31 billion. The 2001 forecast is about $797.41 billion. Additionally, the prediction intervals account for this positive trend by skewing in a positive direction. Once we compute the accuracy measures, it is determined that Holt's method is by far the more accurate of the two procedures. As we can see from this table, Holt's method has smaller values for each of the accuracy measures than does the simple exponential smoothing method. This demonstrates the importance of addressing the influence of trend in time series forecasting when it is present in a particular data set. The next handful of forecasting techniques take into consideration the impact of seasonality on time series. Perhaps the simplest form of seasonal forecasting is the seasonal naive forecast, which is an extension of the naive forecast, as the name implies. With this method, each forecast is equal to the last observed value from the same season of the year. This same season could be the same quarter or month of the previous year, for example. A formula for calculating the forecast for period t plus h would be written as shown here, where m is the seasonal period and k is the number of complete years prior to period t plus h. To demonstrate the use of the seasonal naive forecast in R, a time series that is already encoded into R is studied. This is the air passengers dataset, which looks at monthly totals in thousands of international airline passengers from 1949 to 1960. Not only does this time series display a clear positive trend, but it also displays seasonal variation, with passenger totals being higher in the summer months than in the winter. Forecasts will be computed for each month of the last 2 years, so 24 forecasts total, using the seasonal naive method. Here we have the codes. To get the seasonal naive forecast, we have to use the snaive command, and we set h equal to 24, since that's the number of forecasting periods we want. We don't have to set up a time series, since this example is already set up as a time series in R. This graph displays the time series and the forecasts for those 24 periods. The seasonal naive forecast method obviously accounts for seasonal fluctuations, with the number of passengers predicted to be higher during the summer, just as seen as in previous years. However, because the forecasted values for each month are equal to the last observed value from that month, the increasing trend in the data is not taken into account by this forecasting method. As with naive forecasting, there are generally better methods for forecasting series with seasonal variation than the seasonal naive forecast. One of these techniques is Winter's exponential smoothing method, an extension of Holt's method. This method comprises the forecast equation and three smoothing equations, one for the level, LT, one for the trend, capital TT, and one for the seasonal component, ST, with corresponding smoothing parameters denoted as alpha, gamma, and delta. There are two distinct versions of Winter's method, and the differences between these two models stems from the particulars of the observed seasonality. The seasonality of a certain data set is additive when it does not depend on the level, and it is said to be multiplicative when the size of the seasonal variation is proportional to the level. Because of this, there is an additive version of Winter's method and a multiplicative version. The additive is preferred when the seasonal variations in the series are approximately constant, while the multiplicative method is preferred when they are changing proportional to the series level. Let's discuss the additive method first. Here are the equations for that method. The first equation represents the estimate of the level after removal of the seasonal effect through the subtraction of the seasonal component, ST minus S. The second equation serves to estimate the trend, and the third equation estimates the seasonal effect by smoothing ST minus S, the previous estimate, and the most recent observation adjusted for level, YT minus LT. Finally, the last equation computes a forecast for M periods into the future by combining the level at time t plus M times the trend component's value at time t plus the seasonal component, where P equals 1, 2, all the way up to S. As mentioned previously, delta is the smoothing parameter for seasonality. Turning back to the air passengers example, an additive Winter's forecast is computed by using the HW command and specifying that the parameter seasonal equals additive. As this graph here shows, the additive method may not be the most effective method for creating forecasts for this particular dataset. The forecasts, particularly for the summer months, are nowhere near as high as they are in reality. However, final judgment on this method will be reserved when discussing accuracy measures. For now, let's talk about the multiplicative model. Here we have the equations for the multiplicative method. These equations are fairly similar to those of the additive method, except for a few small pieces. The seasonal effect is removed here by dividing the value of the response at time t by the seasonal component. In the third equation, the most recent observation is adjusted for level through the use of division, and the forecast is computed in the final equation by multiplying the first two components by the seasonal component. In order to fit a multiplicative forecast, we again use the HW command, but in the seasonal parameter, we specify that it's multiplicative. This graph displays the results of the multiplicative method applied to the air passengers dataset. From a purely visual perspective, this variant seems to be more accurate than its additive counterpart, or the seasonal naive forecast. Not only do the forecasts fluctuate depending upon the season, but they also adjust for trend as well. The three seasonal forecasts can be compared using the previously discussed accuracy measures. This table displays the results. As we can clearly see, the multiplicative method has the smallest values for the accuracy measures, so it's probably the most accurate method. It is worth noting the seasonal naive method is more accurate than the additive Winter's method when using these measures. Generally speaking, one variant of Winter's method will always be better than the seasonal naive method, but given the difference between the additive and multiplicative techniques, it is not likely that both versions will surpass their simpler counterpart in terms of accuracy. There are a number of other forecasting methods, including seasonal decomposition, autoregressive integrated moving average models, also known as ARIMA models, dynamic linear models, and profit models. All of these techniques have their own advantages and disadvantages, and all of them warrant exploration and evaluation, which could be the subject of subsequent research. By understanding these additional methods, In conjunction with a thorough comprehension of approaches discussed in this presentation, one can gain a satisfactory grasp of time series forecasting. Throughout this presentation, time series forecasting has been discussed in detail. The aims of forecasting have been explored, and a variety of techniques have been explained. Additionally, it has looked at these methods in R and determined which ones prove more accurate under certain circumstances. This area of statistical study, as highlighted by the examples mentioned in the preceding pages, is extremely important in professional fields, making it of great relevance to individuals interested in data analysis and statistics. Thank you for listening. Here are some of my sources, and here are a few more. Once again, thank you for listening. Have a wonderful day.